Now in this lecture we shall be discussing about the, we can say, basic design principles. Now in the earlier lecture we have already learned that what exactly are the different types of earthquake design categories and for which provision we do need to refer to which particular clauses. So for all the earthquake design categories, that is whether for EDC 1 also, EDC 2 also and EDC 3 also, one clause is common and that is clause 5.2. So clause 5.2 is the universal clause that needs to be applied when we are designing seismic resistant structures in Australia. So the first principle that we are discussing here is that the seismic force resisting system, that is the building structural system that as a structural engineer we do need to plan, do needs to be configured with a seismic force resisting system. Now that seismic force resisting system, either it can be RCC structural walls and the combination of the RCC columns also. So we can say that by adding this particular RCC structural wall, we are adding a very high amount of stiffness to resist the earthquakes. Or a second system may be that we can, let us say if we're talking about the steel structure system, let us say in that particular case, we can add a cross bracing. So that cross bracing can help to control the sway and deflection at the time of the earthquake. So we can say that if we're talking about this RCC system, we can say that these RCC walls, structural walls, they can act as a seismic force resisting system. Or in the case of steel structure, we can say that the cross bracing can be referred for this kind of, we can say, seismic force resisting system. So that is the basic principle of the seismic force resisting system. Now the second thing is that we do need to tie the structure together. Now that is a very, we can say, a basic provision, but just to give you an example, let us say we are dealing with a building here and let us say the height of the building is 20 meters and this is also another column here. So what we do need to do is that more we tie the system, like let us say in this particular case, we do have 3 RCC columns, 3 reinforced concrete columns. So it is not that, it is not recommended to keep this 20-meter high column, we can say, unsupported or untied. We do need to tie these RCC columns with the help of RCC beams. So that is a basic definition of tie. Now we may have like a tie at, let us say, 5 meter, then another tie at, let us say, 5 meter, then another tie at, let us say, height 10 meters. But adding these two ties shall ensure that the structural behaves in a, we can say, integrated manner at the time of the earthquake. So that is a basic provision. And if we are modeling, or we can say if we are constructing a RCC slab also, let us say this is the RCC slab and let us draw it with the help of this. So this RCC slab also ensures that, we can say, that it is acting as a diaphragm. And in addition to acting as a diaphragm, we do add cords and ties also. So we shall also discuss cords and tie in another lecture. But the thing is that when we're talking about the RCC slabs, we do need to ensure that whatever lateral forces are traveling, for those lateral forces we do have sufficient amount of reinforcement. So that is like the basic we can say introduction to tying the structure together. Now the most important thing that we do need to understand here is that I just want to discuss 2 more examples here. One example is that, let us say we are making a building on a loose soil, and on that particular building we are making this particular we can say foundations. Now at the plinth level, this is, let us say, the plinth level or the ground level. This is the, we can say, first floor level, and this is the top level, or we can say terrace level, or we can say roof also, and this is the ground. Now it may happen that we may skip, we may add beams here, we may add beams here also, here also. On the first floor also we may add RCC beams, but as in we can say beginner, we might want to skip adding these beams at the ground floor level also. So that is the like basic provision of the, we can say, code, that we do need to tie the system, especially when the soil is loose, such that when the deflection, or we can say settlement occurs, it occurs uniformly. And let us say in a, we can say in an extreme condition, let us say this column or this foundation tries to settle or come down abnormally. So if a beam is provided here from this column to this column, it shall get activated to ensure that a non-uniform settlement does not occur in this particular foundation. So that is like the basic principle that is given here, that footing supported on piles or spread foundation that are located in soils with maximum vertical ultimate bearing value of less than 250 kPa shall be restrained in horizontal direction by ties to limit differential horizontal movement during an earthquake. Not only during an earthquake, but in the times of the, we can say, occupancy of the building also. Let us say a particular area, let us say this area itself, that is quite heavily loaded as compared to this particular area. So in addition to having a loose pocket here, in addition to having a, we can say, loose soil here, this column may try to settle abnormally. So the more ties we provide, the more uniformly the whole structure shall behave. So that is like the basic principle, or we can say a basic concept we do need to understand when we are doing the structural engineering, that we do need to provide as much ties as possible. Ties can be in the form of RCC slab, it can be in the form of RCC beams, cross bracing, or we can say tie beams. So all those provisions needs to be provided by the engineer. After that, performance under earthquake deformation. So there are two approaches when we do need to consider the seismic resistant design. First approach is that, let us say in this particular building we do have a brick walls here at this particular grade and this particular grade. Now, what we can do either is that we can do either calculate the loading. Let us say the loading is 15 kN per meter. And for this brick wall also it is 15 kN per meter. Now, either in the software we can model these brick walls, this brick wall and this brick wall, or what we can do is that we can just simply ignore all the brick walls, or we can say partition walls, and then just simply go ahead with the code. So that is the basic approach that is given here. So either we can model these seismic force resisting systems such as concrete, masonry, brick and precast concrete walls or panels, or stair walls or stairs or ramps. Now modeling precast concrete wall is always recommended, because it do adds a lot of stiffness for the earthquakes. Panels, modeling panel is also recommended. But modeling, we can say the masonry or brick wall, that is quite difficult, because it do adds unnecessary stiffness also. And we can say that modeling these masonry or brick may have a, we can say, under designed structure, in the terms that the model that you have prepared in your software, that shall have unnecessary stiffness, because in reality these masonry and brick walls shall crack at a time of the earthquake. So as per my approach, it is always recommended that we do model the precast concrete walls, panels, we can model the stair walls also, we can model the stairs also, and we can model the ramps also. But if if you want to talk about my opinion, masonry and brick walls should not be modeled. Or we can say that second approach is that we can model the structure separated from all the structural element, such that no interaction takes place in your analysis, and deflection undergoes, as we can say, a free structure itself, or we can say a sway structure itself. After that, all components, including those deliberately designed to be independent, shall be designed to perform the required function while sustaining the deformation of the structure. So this point is in continuation to this point here, that if you are not modeling the, let us say, masonry wall or brick walls, then those masonry and brick walls need to have a sufficient lateral resistance. How we do provide those lateral resistance? like in some countries where we do use the hollow blockworks, we do provide reinforcement inside the masonry, and that reinforcement, it is usually in the form of vertical mullions also, or in the terms of horizontal bands also. So either we provide the vertical, they are called vertical bands also, or vertical mullions also. Same is the case here also, that either we provide the reinforcement inside this particular brickwork such that the lateral, the capacity of this particular masonry or brick wall, it increases. So after that, we are talking about the floors. Floors shall be continuous over a series of internal walls and should be tied to supporting walls at all the supported edges. So that is a general statement. After that, if we are talking about the, we can say, walls. So walls shall be anchored to the roof and restrained at all floors that provide the horizontal support for the wall. Outer plane forces shall be designed in accordance with section 8. Now what exactly is meant by the in plane and out plane? Let us say this is the RCC wall. So there may be two directions of the forces. One direction can be like in this particular axis, other can be perpendicular like in this particular axis. So this direction here, that is basically in plane, and this direction here, that is basically out plane forces. So that is the difference between in plane and out of the plane forces. That if you're talking about, let us say, this particular RCC structural wall, it has a very high capacity when the force is coming from this particular direction. But if we are talking about the other direction, let us say this is the section, the force is coming along this particular direction, so it may try to bend something like this, and the whole bending moment comes at the bottom, and this is basically the out of the plane forces, because this is we can say a weak axis of RCC structural walls. That is the concept that it is trying to convey here. After that, we have already discussed in brief about the diaphragms. So diaphragm is a term that we are referring to as the, we can say, mostly for the RCC structural slabs only. So we can say that it shall not extend the permissible deflection, and permissible deflection shall be that it will permit attached element to maintain structural integrity and continue to support the prescribed forces. Now basically what happens is that, let us say we do have these we can say 4 RCC columns on the top and on the bottom. So let us say we do have these beams also, and let us suppose this is basically the cutout. This is the cutout. Now when the lateral forces at a time of the earthquake comes, this area, because there is a discontinuity in the diaphragm, this slab is not continuous. This is the slab here, this is the slab here, and this is the slab. Now slab is getting discontinuous here, so there is no continuous diaphragm action here. So it may happens that this particular these columns, it may experience some much more deformation as compared to this column, which is having supported or tied by diaphragm along all the sides. So let us suppose we may have a column here also, and we let us say we have a slab here also. So we can say that deformation at this particular column shall be higher as compared to deformation at this particular column, because the diaphragm is getting discontinued here. So we do have these 3 types of diaphragm when we're talking about the international standards. One is this flexible, second is semi-rigid diaphragm, third one is the rigid diaphragm. So in this case, where we do have a break, we may classify it as a semi-rigid diaphragm. But let us say in a particular example where we do not have this particular cutout here, and we do have a slab here, so in that particular case we do have a rigid diaphragm. So most structures will use the force-based principle of EDC1 or EDC2, except tall buildings where we have to use the EDC3 to consider the higher mode effects. Now new standard also allows the designer to undertake a displacement based check for the earthquake compliance, which is often sufficient in terms of low seismic areas or on rocky or firm soil sites. So major impact of new standard is expected to be low-rise structures, particularly of brittle construction on soft soil sites. Now the first concept that is getting highlighted here in these lines, that we may have a displacement check also. Now what exactly is the difference here? There are these two terms internationally that is used when we're talking about the seismic effect. One is the force based approach, one is the force based, second one is the displacement based. In force based, what we usually do is that we do have a threshold, or we can say a limit on the forces, or we can say that we quantify or analyze the behavior of the structure on the basis of the forces applied. But in the terms of the displacement based check, we do limit the displacement at a time of the earthquake. So by limiting the displacement, we are automatically ensuring that it does not undergo a plastic deformation, or we can say brittle deformation at the time of the earthquake. So that is a basic concept here. After that, if we are talking about the the earthquake design category 1, now this we shall discuss in the next lecture with a practical example.